On November 4, 2025, United Parcel Service Flight 2976, a McDonnell Douglas MD-11F cargo aircraft, crashed moments after taking off from Muhammad Ali International Airport. The accident resulted in the death of the 3 crew members, 11 people on the ground, and left 23 others injured. With the data gathered from the preliminary investigation released by the National Transportation Safety Board, I conducted an in-depth technical review to rebuild the full sequence of events and determine the causes that led to the crash. The McDonnell Douglas MD-11 had completed its standard departure preparations and was cleared for takeoff under normal weather conditions, with no alerts reported by any onboard system. Just after liftoff, as the MD-11 began its rotation, the left engine, engine number 1, separated completely from the wing. It rose abruptly in flames and arced over the fuselage. At the same time, at the separation point on the wing, where the engine and the pylon detached, a second fire was ignited. With asymmetric thrust, and with the high aerodynamic drag created by the damaged structure, the aircraft could not maintain a stable climb. The MD-11 began descending shortly after reaching its peak altitude, with a slight left bank indicating a loss of lateral control. In a rapid, uncontrolled descent, a portion of the left main landing gear struck the roof of a UPS warehouse located at the edge of the airport. The aircraft then continued moving toward an industrial area, skimming over several structures at low altitude, until it finally crashed into a petroleum recycling facility. The impact triggered a violent explosion, fueled by the aircraft's fuel load and structural debris, resulting in the complete destruction of the airplane. The initial sequence of events points to a cascading engine failure as the determining factor in the evolution of the accident. Imaging analysis confirmed that engine number 1, located on the left side of the center pylon, detached during rotation. This separation generated a fireball and a stream of fragments that, after moving across the fuselage, were likely ingested by engine number 2, installed in the tail. The ingestion of solid debris by a running engine results in an immediate loss of thrust or a drastic reduction of it, compromising lift and controllability. The direct consequence was that the aircraft was operating only on engine number 3, creating a critical destabilization at a moment when altitude and airspeed were insufficient for any emergency maneuver. Experts have also identified gyroscopic forces as a factor that helps explain the engine's trajectory after separation. Gyroscopic precession, which acts on rotating bodies, generates movement perpendicular to the axis of rotation. During takeoff, when the aircraft pitches upward, the detached engine would have experienced a rotational shift that pushed it to the right, toward the fuselage, instead of dropping straight to the ground. This phenomenon aligns with the recorded image of the engine, passing over the fuselage and striking external structures, contributing to the ingestion of fragments by the tail engine. Aeronautical engineers note that gyroscopic precession can create unexpected directional changes in rotating components like a falling engine, especially when the aircraft is pitching during takeoff. A key factor in the investigation is the origin of the separation of engine number 1. Early reports indicate the presence of fatigue cracks in the structure connecting the pylon to the fuselage, specifically in the mounting lugs known as the aft lug and forward lug. These cracks developed before the inspection intervals mandated by the manufacturer and the Federal Aviation Administration required a detailed examination. Their early appearance raises questions about the adequacy of current maintenance intervals for such critical structures. Although periodic inspections are designed to detect damage before it becomes catastrophic, the evidence suggests that flight cycle-based intervals may not guarantee early detection of fatigue in components subjected to extreme loads during takeoff and high-stress maneuvers. The initial separation of engine number 1 caused an immediate loss of thrust from engine number 2 due to possible fragment ingestion, drastically reducing the aircraft's available power. With only one functioning engine, the aircraft could not maintain its climb speed or the altitude required for a safe departure, leaving the crew with almost no viable options to avoid impact. An analysis of the forces involved shows that the aircraft experienced sudden changes in structural loading and sharp movements in pitch and roll. The near-instant loss of two engines created a severe lateral thrust imbalance, producing a rotational moment around the longitudinal axis that exceeded the control authority of the rudder and ailerons. Situations like this are extremely critical during initial climb, when available altitude for corrective action is minimal, and the aircraft's speed cannot support aggressive control inputs without risking a stall. Regarding the human factor, the crew responded immediately to the alarms and attempted to stabilize the aircraft, demonstrating that emergency protocols were executed correctly. However, the combination of thrust loss and the aircraft's proximity to the ground made any corrective maneuver extremely limited. Despite the professionalism of the pilots, the magnitude of the structural failure and the loss of power could not be overcome. The NTSB preliminary report explicitly cites the crash of American Airlines Flight 191, a McDonnell Douglas DC-10 that crashed on May 25, 1979 in Chicago, as a significant precedent. Both aircraft belong to the same design family, with the MD-11 being a later development of the DC-10. In both accidents, the left engine and its pylon separated during rotation, and in both cases, the loss of the engine triggered an uncontrollable left roll. In the DC-10 accident, investigators found that a 13-inch fracture caused by an improper maintenance procedure was responsible. In the MD-11's case, preliminary evidence suggests fatigue cracks that developed over the aircraft's service life, even though it complied with the established maintenance program. Beyond the technical aspect, the investigation highlights the importance of design and inspection of engine mounting systems. In aircraft like the MD-11, engines mounted on pylons are subjected to torsional and vibrational loads during takeoff, in addition to aerodynamic forces and engine weight. Over time, these loads can lead to microcracks that, if not detected early, propagate and result in a complete separation of the engine. Reviewing inspection protocols is essential to ensure that critical structures are evaluated effectively and safely, even before reaching the flight cycle thresholds that typically trigger deeper inspections. This has been the full reconstruction of the United Parcel Service Flight 2976 accident. If you enjoy this type of video, you could leave me a like and subscribe to the channel, and that will help me keep creating content, and it will also keep you up to date with everything I upload. Before wrapping up, I'd like to know your opinion in the comments, and hear whether you think this accident could have been prevented. Thank you. I'll be reading your comments, and I'll see you in the next video.